Hello and welcome to Lecture 9 of Math 2R03. In today's lecture, we're going to look at section 3.A of the textbook, where we're going to learn about vector spaces of linear maps. So before we get into the details of today's lecture, I just want to kind of highlight that there's kind of a theme in mathematics that not only applies to linear algebra, but to many of your courses in math, where we first introduce objects, and then what we're interested in is about maps between objects. So in calculus, you learn about the real numbers, and then you have maps between objects, which are functions that take numbers from real numbers to real numbers. Now in linear algebra, the objects that we're interested in are vector spaces. And the other thing that we want to study is once we have the notion of a vector space, we want to look at maps between vector spaces. And that's kind of the topic of today's lecture, which is linear maps. So we're starting our discussion about maps between vector spaces. So as I just said, one of the goals of today's lecture is to introduce linear maps. Okay, and linear maps are special types of functions between vector spaces. So you have seen a linear map in Math 1B03. We would have called it a linear transformation. So different textbooks call it different things. So in this course, we call it a linear map, but you could think of it also as a linear transformation. And a linear map from a vector space V to a vector space W is a function that goes from V to W such that the following two properties hold. First, that we have t evaluated at u plus v is the same thing as t first evaluated at u and then added to whatever we get when we evaluate t at v for all vectors u and v inside of capital V. And so we call this the additive property. So our function has the additive property. So the order in which we do our operations, do we first add our vectors and stick it into our function, or do we stick our vectors into our function and then add the resulting output? It gives you the same value answer on both sides. The other property that we have is how scalar multiplication behaves through our linear transformation. So if I take a vector and first scale it by lambda, it's the same thing as first sticking my vector u into the function and scaling it by lambda on the other side. And this holds for all vectors u in V and lambda inside of my field F. And this is called the homogeneity property. Homogeneity property. Oops, let me respell that. Homogeneity property. So again, just let me reiterate, we've seen this in Math 1B03, and what we're going to be looking at in this chapter is looking at these maps in more detail. Now, one thing that you want to pay attention to in the book is that instead of writing t evaluated as u with these parentheses, they usually write it just as tu. Okay, so just remember what that means is that you're taking u and you're sticking it in your function t. So it's doing a little bit of abbreviation. It's not including the parentheses inside of there. And we come to kind of the most important definition from today's lecture is this set LVW. And what this set LVW is, it's all linear maps from V to W. So you look at, you fix your vector spaces V and W, and then you look at all the linear maps that go from V to W and you stick it into this set. So this is a set of functions that go from V to W. So in the next couple examples here, I want to show you some examples of things that live inside of this set LVW. Okay. So one example, regardless of what vector spaces that I'm looking at, is the zero map. Okay, so what is the zero map? Well, the zero map is the function that goes from V to W defined by taking any vector inside of V and you're mapping it to the zero vector inside of W. Right? So let me just point that out. So this is the zero vector in W. So it takes any vector v in V and it maps it to the 0 vector in W. And remember, this is a vector space, so this vector space has a 0 element. And then you can check, right? So the fact that 0, this map, is a linear map. Okay, so it definitely belongs inside of this set. And it definitely has the additive property. If I take U plus V and stick it into the 0 map, I get 0 on the left-hand side. And if I plug in U, I would get 0. I plug in V, I would get 0. And 0 plus 0 is 0. Okay, and the same thing would happen on the other side. So for any V and W, I have always the 0 map inside of this set. What else do I have? Okay, well, in the special case that V and W are the same, right, then the identity map, here, maybe I should make this a little bit clearer. This is the set of all linear maps from V to itself. The identity map is in this set. And this is the function that goes from V to V, defined by taking any vector V and mapping it to itself. Okay, so it's kind of a very boring map, but this is an example, okay, of a linear map. So fact I is a linear map. So these gives you two examples of linear maps and gives you examples of things that belong in this set, L, V, W. And let me give you a more complicated example. Okay, and this is a very interesting example because it uses calculus, and you're going to see that what you were doing in calculus was actually examples of a linear map. So we're looking at the special case that V and W are the set of all polynomials with coefficients inside of R, right? So this is all polynomials with coefficients in R. And we're going to define a map that goes from all the polynomials to all the polynomials, and it's going to be defined by taking a polynomial and then you differentiate that polynomial. Okay, so we take P to its derivative. Okay, so just remember on the left-hand side are all polynomials, right? And you're mapping it to the set of all polynomials. And the way that you're doing it is you're taking your polynomial and you're mapping it to its derivative. And this is a linear map via the properties of calculus. Okay, so something that you would have learned in your either your Math 1X or Math 1A course. And why is that? Well, when you take the derivative of the sum of two functions, right, from calculus, right, you're taking the sum of the two functions. That's the same thing as first taking the derivative of P and then adding it to the derivative of Q. But that's the same thing as first the function applied to the function D applied to P, and then taking the function D, applying it to Q. And scalar multiplication is the same. If I take a polynomial and I multiply it by a scalar and I ask for its derivative, well, that's the same thing as first taking the derivative of the polynomial and multiplying it by the scalar, right? So I can rewrite this as lambda times the derivative of P. Right? So these are properties that you would have seen from calculus. So here are some examples of linear maps, okay? And what we see is stuff that we've been doing in calculus really was also an example of a linear map, but you just wouldn't have called it that. We'll do another example from calculus in a minute, and then we'll dive a little bit further into looking at the structure of this set that we introduced over here of all linear maps. Okay, so we'll pause right there and I'll see you in the next part.